So in the inductive step of the proof, we assume that for a particular integer k greater than or equal to 4, that this inequality holds, parameterized by k, that 2 to the k is greater than or equal to 3 times k. And we use this fact to show that the same equality for a value of k plus 1 holds, that 2 to the k plus 1 is greater than or equal to 3 times k plus 1. The inequality using the value of k, which we are assuming to be true, is called the inductive hypothesis. Now, the way we show that this inequality is true is that we start with the left-hand side and show that this expression is greater than or equal to some other expression, which is in turn greater than or equal to some other expression. And after a sequence of steps, we end up with the expression on the right-hand side of the inequality that we'd like to prove. Now, if all of these inequalities are true, then the left-hand side is in fact greater than or equal to the right-hand side. It's okay to have an equal sign at one or more of these intermediate steps, because at each step we just need to show that each expression is greater than or equal to the next expression. Now here are the steps of the proof filled in. The first step is to separate out a factor of 2. This equality holds because 2 to the 1 times 2 to the k is equal to 2 to the k plus 1 because the exponents add. The next step is where the inductive hypothesis is applied. The inductive hypothesis says that 2 to the k is greater than or equal to 3k. So we can replace 2 to the k in this expression by 3 times k, and the resulting expression is less than or equal to the previous one. It's important here that the coefficient 2 is positive. Looking at it another way, we could start with the inductive hypothesis, which says that 2 to the k is greater than or equal to 3k, and multiply each side of this inequality by 2. Since the multiplier 2 is positive, the inequality will still be true, and so 2 times 2 to the k is greater than or equal to 2 times 3k, which is exactly the inequality that we have in this second step. The next step is an algebraic step. 3k plus 3k is equal to 2 times 3k. Now the next step is using the lower bound on k in the inductive hypothesis. The inductive hypothesis holds for k at least 4. So if k is greater than or equal to 4, it's certainly greater than or equal to 1. We are effectively replacing a factor of k in one expression with a factor of 1 in the next expression. The resulting expression is less than or equal to the one that came before. Looking at it a different way, we can start with the inequality that k is greater than or equal to 1 and multiply both sides times 3. Since the multiplier 3 is positive, the inequality still holds. Then we can add 3k to both sides. The resulting inequality says that 3k plus 3k is greater than or equal to 3 plus 3k. And this is exactly the inequality that's used in this step of the proof. In the final step, we pull out a factor of 3 from both terms, resulting in 3 times k plus 1. And this is exactly the expression on the right-hand side of the inequality that we wanted to prove.